Harry, hi everybody. Tom here. Jim's just getting stuff queued up. I mean, the objective today was to basically help folks who were relatively new to GAMS to sort of get oriented toward general equilibrium modeling and how this works, which I think is always, Jim's very good at sort of relating what we do to what the underlying theory is. He tends to focus more on smaller models.
Is muted, it looks like. There is no, oh, it looks like you're unmuted now.
Great, thanks. Thanks a lot. So Jim is just we're gonna take, I was just gonna explain, I sent along this morning, or Martha sent along some exercises that are complements to what Jim had been going through. And then in Jim's lecture, he made some comments about sort of optimizing over equilibrium systems. He made a couple of references to that, and those weren't covered in his exercise. So I thought that I'd put together a little exercise that illustrates how that's done. So this is intended primarily, I know there's a number of audience members that perhaps have been through equilibrium modeling before, and you've seen this stuff. You've already worked through Jim's examples. And so I thought for those folks, I'd provide a second example that would be something else you could work on as part of the this sort of workshop. It's also an opportunity. My brother-in-law was he went to Harvard Business School, and he used to refer to it as tire biters. Tire biters is an expression from HBS that describes students who are like dogs. They like to chase cars and bite the tires, right? So if you're a tire biter, this is an exercise that gives us a chance to sort of discuss things. So I thought I'll just take 10 minutes, go through the exercise, and then tomorrow we'll pick this up at lunchtime tomorrow to compare notes. It's also one of the things I like about equilibrium modeling is that it provides a framework for assessing the plausibility of arguments. And it's not something that provides a single number, but it provides a framework for thinking through the logical consequences of policy. And I thought Jim's sort of reference to the MPEC example was provides a nice sort of framework for thinking about how it might work. So here I'm going to think about a problem which is looking at oil markets, something that's sort of in the news these days. So we think about there being some countries produce crude oil, and then countries also refine crude oil into refined products. So we have these two sort of interconnected markets. And I wanted to think about a model where you have a set of coalition states and a target state. So the objective function here is to think about interventions in the form of taxes on crude oil trade, which seek to punish a target region. So the idea is, what tariffs do we apply on crude oil that will minimize the value of that country's net exports, where the coalition states are a subset of the full world. So this is a sub-global coalition. So in the example here, I'm just doing one of the things that's great about GAMS, for those of you who have not used GAMS, is that GAMS provides a framework for separating what's the theory of what am I doing from what's the parameters and the numerical values of the problem I'm working on. So we can work through the theory first just with made up numbers, but then we have a model, and then we can pour in real numbers and see how that changes things. So here I'm going to say, okay, well, let's suppose we have 4 regions in the world, R1 through R4. And I'm going to let R1 be the target of the sanctions. And I'm initially going to think about the coalition region being just R2. So of course, you could have R1, you could do this by defining, we could, for example, I'll just make a note here, could alternatively have set R could be Russia, Europe, USA, Japan, right? You could have India, you could have China, right? So you could basically fill in a set of regions of the world. There's no change in that. That doesn't change the function. It just is a data change in the program. And then the coalition here could be more than one. So it could be, e.g., our coalition of R could be, for example, Europe, USA, Japan, right? And now what's the minimalist model? So what I like is what's a minimal model for looking at this idea? Well, we could have aggregate price elasticity demand for oil products. So that's the price elasticity demand for gasoline, fuel oil, heating. This is a model where I don't distinguish between oil and gas, but it's just hydrocarbon demand. And there could be an aggregate elasticity of supply for crude oil. And then we could have elasticity of substitution across crude oil varieties. This is a case where we make this Armington assumption, and we're going to lean on this idea that refineries are designed for using particular types of crude. And so therefore it's not easy to switch. It's not just penny switching from one type of crude to the other. The sourcing of the crude depends. So certain US refineries are set up to refine Venezuelan or Canadian tar sands, and other refineries are set up for light. So there's differences that are defined that define that elasticity. And now we've described the world as we see it. And again, this is very similar to what Jim's exercise this morning, talking about his micro-consistent matrix. This is a much simpler Marshallian model. So all you need to know is what's the value of benchmark demand for refined oil products? What's the benchmark supply of crude oil from each region? What are the benchmark trade flows? And that includes flow X0 of R, R is the production of crude oil in R that gets used in region R refineries. So that has all of those guys. So here I'm just gonna, and so what I have here is a random assignment, but in principle, this could be calibrated to real data. The one thing when you calibrate the real data, these numbers are not in millions of barrels per day. We're using what's known as Harburger units, where the prices of all the goods are equal to one and the quantities are what $1 worth would buy. So that's the simplification we have, is using Harburger units on the trade flows. And so now we write down a model. And that's the whole idea here, is about equilibrium modeling, is combining what we observe about the world as what we observe is going on in the world, and then some theory that explains what's going on in the world. And then we want to ask questions of that model. And so it goes beyond. A lot of policy analysis is driven by what is about the world, what is the data that tell us. But here we want to go beyond that. We want to think about what would happen through intervention. So this is the model we think about as one where supply in region R is a function of what the value is. C of R is going to be the supply price in region R. It's the marginal cost of production. And this is a supply response, which is assuming competitive supply. And then we have a demand response where epsilon is the price elasticity of demand. P of R is the price of refined products, and D0 is the benchmark supply. These are both using sort of a calibrated share form. So when C is equal to 1, Y is equal to Y0. When P is equal to 1, D is equal to D0. And then we have a market clearance constraint that says what gets produced in region R gets shipped to other regions RR. So X and Y are related through this market clearance condition for the output from region R. And then we bring in a little bit of theory. So the theory we bring in is that goods in different regions are imperfect substitutes, and the elasticity of substitution is given by sigma. So sigma determines how easily it is to move between. So that describes how easy it is to retrofit refineries in India to use oil from Russia rather than oil from the Middle East. So they may have refineries that are set up to refine sort of light sweet crude, and they want to be able to move over to using heavier, sour, whatever. So there's the differences. And this is, I admit, this is completely sort of, I'm writing down a theory with numbers experiment that captures this idea. So I don't really know what sigma is. I would imagine the number is high, like 4 or 8 or something like that, but I don't really know the number. But we're not trying to search for the truth. We're just trying to provide a feeling for what the range of possible values are. Because now I'm going to say the price in region R of refined products depends on the price of the inputs, and the input prices is what they pay at the supply price. C of RR is the supply price of crude oil from region RR, and then I'm going to apply it times 1 plus T, where T is the tax rate applied. So here we're going to think about there being, and that's the strategic instruments that are going to be adopted are tax rates on trade. So this is not going to be, we're not going to like cut off all traders to apply a tariff on the imports. And so then we have an equilibrium problem we write down, which has got demand associated with D, markets determining the output price. The supply determines Y, that's Y is a defined variable. Inputs, again, determines X, so that's a defined variable. And again, P. So we really have just this, the one equilibrium constraint is really just a market clearance condition that determines the market price. And all the rest of the variables in this model are simply assigned or definitional. So now we write down the model. And again, this is something that Jim skipped, but I'll just explain it very quickly. When I write down a model, I want to have a benchmark equilibrium data set. I want to verify that the data I have is self-consistent. So I assign what I think to be the variable solution values, which I assign D and Y and X, and I assign, oh, this could be, here I have X, so I've defined it X0, so this could be X0 of R. So I assign my benchmark values, I assign the prices all equal to 1, and then I say solve. And then I'm going to say abort, that means stop the whole process if I don't have a precise solution. So that says if the deviation is greater than 10 to the minus fifth, then stop it. And so once I've done that, then I say, okay, now I'm going to write down an objective function that says target the value of sales. That's the shadow value of sales from the target region. So I sum over the target region of the value of output times the same. So here I'm saying I want to design a set of tariffs in the importing country, that's the coalition country, which minimizes the value of the sales from the target country. So there I said, and I'm going to put that in, and I'm declare that model as sanctions. That includes all the equations, including the objective function. That's a shorthand in GAMS to say to throw all the equations in. I put an upper bound of 20 just to avoid bad function evaluation. So I say, okay, well, let's put in, say the maximum rate is going to be 2000%, which I don't think we'll get to that. And then I say, well, solve sanctions using nonlinear programming, minimizing the objective function. Then I say display OBJ. If I run this model, again, I tend to be old fashioned, so I run GAMS from the command line. Say GAMS sanctions. That gives me a solution. You see, this is a trivial little model as I've currently done it because it has very small dimensionality. If I look at the bottom, here's what, if I look at bar T, the optimal tariff rate will be 120% tariff rate. So that's going to be on from region 1 into R1 into R2. And then this shows what happens. Trade flows from R1 into R2 go down by 98%. Trade flows from R3 and R4 go up by around 20%. There's a reduction in exports from R2, R3, and R4 to all of the regions except they basically compensate. They're the ones who are going to be, so that shows what happens to trade. The price goes up by 5% in the coalition states. It goes down, goes up by, let's see, what's it going down here? It's going to be, I don't understand exactly that. Anyway, there's stuff I'm not sure. It's a solution by, I haven't examined in detail, but basically the value of the output goes down by 5%. And I didn't report what happens to P times Y. So let me just, so that's going to be, if I do that, I'm going to just, and again, this is the way it works. You say, okay, let's look at, if I do a percent here, it's going to be P times Y, which is, and so this will be P dot L times Y dot L of R divided by Y0 of R. So that's looking at that's the change in the value of sales. So if I rerun this, because that's what gets minimized. If I look at P times Y, we see that this shows that the value of crude oil sales from region 1 goes down by 0.5%. The value of crude oil sales by region 2 goes up by 6%. and so forth. So that shows what the changes are, and that changes what happens to the demand, and that shows what happens to output. So this is a nice example. What I'm trying to just show is that what Jim went through this morning with very, very like X, Y, and so forth, it's relatively simple to take a few ideas, a little bit of data, and do a calculation. And the beauty of this idea, and this was something that Jim taught me when I first tried to learn economics, he kept saying, keep it simple, right? Just like get the idea across. And so the idea is that just keep the model simple to focus on what the idea is and try to draw as much insight from that as you can. And so the first thing is, when I try to develop a model, I first forget about the numbers, just get the logic down, verify that we have a solid model that actually we can compute, right? And then we give the tire biters in the audience a chance to demonstrate their chops. So here, the assignment is parameterize this model with benchmark data on crude oil supply, refined product demand, and bilateral trade flows. So go out and find some data, okay, to show you. And if you want to look for data sets, I would look for, you could go to XEO base, or you could go, so you could basically, if you have GTAP, you could go to the GTAP trade flows, whatever. Calculate, sort of put in the parameters, define the regions to be real regions, and investigate how the optimal tariff depends on the elasticity of demand supply substitution, as well as the size of the coalition. So this is a model which is just, I mean, honestly, I just did it over in a 10-minute, I was just listening to Jim's lecture. I thought, oh, this would be nice to do a little example to illustrate how this works. So it's a very simple model. So what we'd have is, it's a chance for people to compare things. And one of the things I like about it is you have a plausible idea. We're all sort of trying to solve the same question. I'd be curious as to how much difference we get in results across different students, have different data sources, different takes on elasticities. How much commonality and difference do we have of the conclusions we get from this? So I thought we might discuss this tomorrow. If you want to submit, if you want to do a calculation, send me your GAMS file. Then tomorrow at lunchtime, I'll have a look through what we've got, and I'll report after lunch tomorrow. I'll report back what the similarities or differences are across the results. So those of you who are in, and this is not intended, the people who haven't, if you've not programmed in GAMS, this is perhaps too advanced a question, exercise. But if you have before, then you want to play the game, this is an opportunity for you to sort of parameterize. So I'm giving you very little, it's just sort of a blank slate, and it's a chance for us to sort of do something that's kind of interesting. That's, I would argue, is sort of, in the current state of affairs, is relatively policy relevant. It's kind of, it's always amazing how simple insights can oftentimes be. I mean, Natalie and I were talking about this, anticipating ex ante what the question is. Ex post, you can always explain what's going on, but ex ante, what does the model tell you? And I think this is an interesting one in the sense that you think about, well, is the optimal tariff actually infinity, or is the optimal tariff something less than that? And this model, I think, would suggest that it's probably less, but we could see how that goes. So I'll pick that up tomorrow. I will.
I had to exit to be able to do my own work to prepare, so yeah.
Okay, you're back.
Yeah.
Now you need just to start sharing.
Yeah. So we're back to simpler stuff. And I wanted to talk about a couple of variations on the model, sort of sticking with the model I presented before. Sorry, I'm over here on this one. To show you the importance of general equilibrium and the importance of modeling choices about how you do something, because sometimes people say, well, I don't really know how to do it this way, so I'll do it this other way. And you actually, I'm going to show you, you could arrive at very, very different counterfactual predictions from the model, depending on the choices you make. So this is the same model we did before, and I wanted to point out as one little extension, the difference between modeling a tax versus a real transactions cost. And it's going to be a specific kind of tax. It's just going to be, the revenue is going to be lump sum redistributed to the consumers. It's still distortionary. There are 10 million consumers. What you pay in tax does not, you only get 1/10 millionth of that back. So it's taken as exogenous by the consumers. The reason I'm doing this one is there has been, or at least in the distant past, there was a lot of tendency to convert all kinds of costs into ad valorem tax equivalents. And I'm going to show you that that could be wildly off from modeling it in a more accurate kind of way. So this is our little two-factor example in the Hicksian framework where utility or welfare W is treated as a produced good. And I'm going to introduce two additional parameters. One is an ad valorem tax on the inputs into a sector. And the second, TC is like a transport or trade cost. Trade is not explicitly modeled here. I'm trying to keep it as simple as possible. But some of the output disappears between the producer and the consumer. I thought I had notes, writing out this in slides, but I can only find it for another trade model example would require starting all over again. So I'm sorry about that, but I'll try to illustrate what's going on. So the modification in the equation that I showed this morning is this one right here. The marginal cost of production is the price of labor, price of capital to their share exponents. And then there's a transportation or iceberg cost and a tax, which is TR, or which is sort of like tariff, TR. And those are markups, those are ad valorem markups. I've assumed they're multiplicative. You don't need to do that. So the tariff would be marked up on the transport inclusive price, although I'm not going to have them both positive at the same time. So it doesn't really matter. One of those is always going to be zero. So when you look at this equation, you think of it in a partial equilibrium framework, these look like the same things. Okay, doesn't make any difference. We'll just treat the transport cost as if it was a tax or vice versa. However, they both appear somewhere else in the model if it's going to be a consistent model, and therein lies the difference. Where do they appear? Okay, so for this TR, the tariff or tax rate, redistributed back to consumers. So where that appears again in the model is in the budget constraint, the income constraint, that is. Income equals the revenue the consumer derives from selling labor, from selling capital, and redistributed tax revenue. So this is marginal cost, PL to the 0.25, PK to the 0.75, times the tax rate, times the output level of the good is tax revenue, right? So that goes back into the consumer. The idea behind iceberg trade costs is it's a simple way of modeling a transaction cost or trade cost in that it's assumed to be in units of the good itself. So the idea behind the word iceberg is that as the iceberg goes from the origin to the destination, it melts. Part of it shrinks and the cost is in the units of the good itself. And that's an economical modeling assumption, in that you don't need to model a separate transportation technology, which would be a good idea, but it's a shortcut to avoid having to do that. The thing to remember about it is it's kind of an ad valorem concept, if you might have a model with many goods and the shrinkage rate, the melt rate is the same for all sectors, you're going to get wildly different actual if you have a container full of wheat versus a container versus microprocessors, iceberg trade cost would say the shrinkage is the same in both cases, say 10%, but the actual dollar value would be dramatically different. Okay, so it's kind of assumption that people are not very careful about, but I just want to show how that works. So there's no terror. So if TC is positive, there's no there's no tax revenue to be redistributed, but this TC does need to appear in somewhere else in the model, or the model is going to be inconsistent, and you're going to get a solution that has positive marginals on positive variables. Something is going to be wrong. So where does this transportation cost appear elsewhere in the model? Well, in this, it would appear here. And what's going on is that if X is defined as the amount produced by the production sector, then the amount that actually arrives to the consumer is X divided by 1 plus TC. So the amount produced, X, shrinks by this factor 1 plus TC. And so in the supply demand equation, what has to appear is the amount that the consumer actually gets out of the amount that's produced. So for a general equilibrium solution, it's one or the other. Well, of course, they could be both there. But what I'm just going to show you is that the difference of this is dramatic. And often, at least in older general equilibrium models, just converting things to ad valorem equivalents might dramatically underestimate the effects of the policy that as it really exists. So anything that actually destroys output, transportation costs, bureaucratic procedures, maybe there's red tape at the border that generates no revenue. But, things are held up for days, filing forms, hiring lawyers, hiring accountants that could be doing something else productive, should be modeled in this way. Okay, so now I'm going to have to. So what I do in this model, and this is an example of how to do sets and scenarios. I was going to do a simpler version of that later. This is a scenario. Oh gosh, how much to do on this? I don't want to give too much detail. These are resources here for you to use for. But this is an example where we're going to iterate over different levels of this cost. And for each level of this cost, we're going to compute the solution for one, if it's a tax tariff or if it's a trade cost. So this is going to be a double loop over J, which indexes the scenarios for set T, which is 25 different levels of trade costs or of this variable TC or TR. So I've written it as two separate loop statements here, which is GAMS notation, although you can write it as loop double percentage J comma T. You don't have to do it this way. When you make a new pass through the loop, set them both to 0. This is important because otherwise parameter changes are carried forward if you don't set them back to where they should be. And this then sets this rate of equal to 0.5 times the ord of T minus 0.5. So the first one is 0. Now, ord of T is just a GAMS command that turns a set index into an actual number. There's another way to do this, but I can't quite remember what it was. But you can't multiply, even if the elements of a set are numbers, you can't multiply by the set index. It's a logic, it's some logical way, you can't do it. But you can convert the ordering of the set, the ordinal of the set, into an actual number with this command ord of t. So then for the first element of set t, ord of t is the number 1, and you can add, subtract, multiply, and divide by it. And so this is the way I always tend to do it because it's fairly simple. So ord t is just going to iterate up through all levels of this, this trade cost or tariff. And then it'll do it again for, if it was the trade cost first, then it's going to do it for the tariff and vice versa. The next two things are useful conditional. Again, there's several ways of doing this in GAMS, but the $ operator is like an if statement. You can also do this with if else statements. But the $ operator on the left says TR is going to equal this rate if the ordinal of set J is equal to 1. So in the outer loop over J, if it's in J equal 1, it's going to set the tariff rate TR equal to rate of T. But if it's a trade cost, so the ordinal of J is equal to 2, it's going to set trade cost equal to that rate. When the ordinal is on the left, the conditional is on the left in GAMS, it means set it equal to the right-hand side if the conditional is true. If the conditional is false, leave it unchanged as to what its value is. And so that's why in each pass through these loops, reset these things to 0. So if the conditional is false, it puts it at 0. Actually, I could have put the conditional on the right. We never know where to stop. Keep teaching you little things about GAMS, but otherwise it gets, if the conditional is on the right-hand side, so if it said rate of T $ or J equals 1, same thing happens if the conditional is true. If it's false, it sets it to 0 rather than leave it unchanged. So there's actually a difference in GAMS, whether that conditional is on the left-hand side or the right-hand side, if the conditional is false. I know that's very fast, but maybe you can stick it somewhere in the back of your mind. Solve the model, extract welfare into a parameter that's defined over those two sets, and then close the loops, close the inner loop. And when that's exhausted, it goes back and does the outer loop again. And so it will compute this solution to the model 50 times, 2 times 25. So below that is just extracting a parameter so you can make a nice little table, little matrix of the results for this. So what we've got here is results over set T rate. The first column of this little matrix will give that the rate. And then the second column gives welfare under the tax scenario, and the third column gives welfare under the transport cost, the iceberg cost. Option results : 6 semicolon. I have no idea where that came from. What's this line, Tom?
Is it display results with 6 decimals of precision?
Oh, I didn't put that. I didn't know that.
The default is 3.
Yes, the default is 3. I don't remember. I didn't know what this. I don't know where this came from. Maybe somebody else was messing with my code. Okay, and then display results.
What's
And
the
again, this
division
is
by
in
200?
other materials I have. but this is the code. The last two lines are the code for dumping this two-dimensional parameter, this little matrix, into an Excel file. And this uses a utility called GAMS Data Exchange, GDX. And it's really quite powerful, but it's very, very hard to remember the notation for this. It drives me nuts. I have to look it up every time I do it. Just
That changes too.
yeah, it changes too.
What's the division by 200 for? Is
Sure.
that the initial welfare level?
Is asking whether there is a particular logic
Oh.
to ordering the indices.
No. I could have done it the other way. T could have been the outer loop in this case. Well, there may be, I shouldn't make that a blanket answer, I guess.
So no, it's kind of welfare TG instead of welfare GT. That doesn't make a difference, right?
Cool. Say that again?
It's the question how a parameter is defined, whether I define welfare of T comma J instead of welfare J comma T. That is the same. Is that correct?
Yeah, yes.
So it doesn't make a difference how you order the sets.
Right. I could have, yeah. That's right. It could have been the other way around, if that's what you're asking, with the labels first. Then you're, instead of having something that's 3 by 25, it's going to be
25 by
3. Yeah. Yeah, so
It
whatever.
doesn't matter.
Yeah,
either way.
that's right. That's
Just
correct.
the question of one of our
Yeah.
participants.
That's right. So those last
And
two lines, again, just
The
for you,
division
you know,
by
you can-
200,
You'll need to look this up or you'll see it on many of my examples.
Hmm.
I don't want to have to explain GAMS data exchange. You really don't want me to try either. The first line is actually requires 2 lines of code. The first one dumps this parameter results, and you don't put in the set indices there. Dumps it into a GDX file, and the second command dumps it into an Excel file. So I think GDX XRW took me a long time to figure out that that actually means something, because they don't tell you in the GAMS manual. I think it stands for GAMS Data Exchange Excel Read and Write. If it doesn't, that fits anyway. That's how I remember what it is. There's nowhere in the GAMS code, the GAMS user guide, that tells you that that's what that means. Like you go, what, GDX XRW? Anyway. All right, so I'm just going to show you when you dump that, and then you can use Excel to make a diagram. So I'm going to have to go to a different file here. So this, when you dump it to Excel and you get a, I can actually run the code and show you. And you get this, and then you put in an Excel file, and you can use the Excel file then to make a diagram, make a chart. What you see here is there's going to be a dramatic difference between whether this distortion is treated as a tax or as a real transactions cost. Okay. The tax, and we frequently find this in general equilibrium model, these taxes that are redistributed along some of the consumers. Often even, you know, a tax of 10% or something turns out to have tiny welfare effects. They're really, really small. And in fact, if your micro theory is good, you know that at 0, that tax curve has to actually be flat, okay? That's a consequence of the envelope theorem. You're at the, 0 tax puts you at the top of the welfare curve. So when you first put on a little tax, there's not, you know, it's actually flat. The first order effect of a tiny tax is 0. Okay.
So there's a pre-existing taxes, we'll change that. If there's a pre-existing.
Yes.
if we're playing
Oh,
around.
yes. Yeah. Then you're not at the,
Yeah.
then 0 tax is not at the top of the welfare curve. And there's cases like where you have distortions like monopolistic competition, where the top of the welfare curve is actually at a negative tax.
Right.
Okay. And I have an example of that in my model library. I remember Tom and I in the sort of 80s or at least some of us that weren't GE model, not Tom. Those of us with GE models used to joke that the answer to any question in an applied general equilibrium model is 1% of GDP or 1% of welfare. And it's partly this effect that a lot of things were modeled as ad valorem equivalents with redistribution. And you're just almost guaranteeing from the structure of the model that you're going to get very, very small welfare effects. The real transactions cost, though, is much more powerful. You don't get this money back. Output disappears. It's sort of like negative technical change or something. And you see that curve is negatively sloped even at 0. It goes down much steeper than the taxation. So this is just one illustration of many things that, that theory should kind of guide modelers to try to get as realistic as possible when you incorporate added features into the model. If you think that this is a real cost, there's a regulatory red tape burden, or anything that's not resulting in revenue, don't model it as a tax equivalent. It's only a tax equivalent at 0. And after 0, it's not. Okay. So that's the first thought for the day, that theory really should be guiding GE modeling as to what is the correct way to model policy interventions. Okay, so I have to go back now to, yes. You want me to, you don't want to use this diagram, you want to go, okay. Okay.
I guess you would divide it by 200, so you could normalize to 1.
Yes, correct. Yeah.
Okay. And the second comment was 200 is the no tax level of welfare.
Yes.
So the second comment is correct.
Yeah. So when displaying things like that, sometimes if you have, crazy units, it can be just easier to look at a chart or interpret when you have some kind of normalization or put it in percentage. Yeah. So also when you normalize something to 1, if it goes up 10%, it goes up to 1.1. It's easy to say, oh, that's 10%. Whereas if you start with numbers, 200 is a nice round number, but in many cases the numbers might not be, might have, 211.136, and what's 10% added to that? So just it's simple. It's just an expositional normalization. It's not at all necessary for anything else, but I think easier to read off the chart right away when things start at 1. Everything is a percentage change. You can see what happens. Okay, so the second example, again, the idea here is to try to keep things as tight with theory as possible, is the difference between an intervention that's a tax, which is an intervention on the price side of a market, versus something like a quota, which is an intervention on the quantity side of the market. And the lesson here is you can always calibrate a model so that they're the same. And I know in the early days of CEG modeling, there was a tendency to take any non-tariff barrier and just convert it into a tariff. All right. And I'm also going to say that there's no reason to have to do that. that it's easy to model it correctly as a quantity intervention. And like in the previous example, as you start changing on parameters, then doing counterfactuals, the results can look very different between the two of them. Okay, so this again is our same exact model. But in one case, and there's several ways of doing this, which are in my model library. What I'm going to do here is in fact treat a quota as a tax equivalent, but the tax is a variable because as you change other parameters in the model, the tax rate that would enforce that quota keeps changing. Okay. And that's where another place I'd like to use the whiteboard, but we can't do that. Okay. I should have a diagram for that. I probably do in some of my other notes somewhere. So QR is going to be a tax equivalent that enforces the quota, and TR is just the tax rate itself, as before. So in the pricing equation, where do these things enter? Well, again, as in the previous example, they enter symmetrically. In the pricing equation, marginal cost times 1 plus QR or 1 plus TR is the marginal cost inclusive of the distortion greater than or equal to price. So they appear again completely symmetrically. They appear from that equation as looking identical. And now in this case, actually, they both generate revenue, say. Think of the quotas as licenses which are sold to people wishing to purchase this good, little slips of paper that says you're entitled to purchase 1 unit of this good. So now they also enter symmetrically in the budget constraint. Okay. They both generate revenue. And so again, those things look completely equivalent. However, the difference in this case is that QR is not a parameter, it's a variable. So QR appears as a variable in the list of variables. Actually, it could be potentially be a free variable where it could take on negative values. It doesn't necessarily have to be a non-negative value. So it's now a variable. The tax rate always has to be adjusted to hit the quota level to enforce the quantity restriction. So it's an added variable, so it needs an added equation. So that's the added equation down here is called quantity constraint. I guess the name I just made up, quota, which is a parameter, the amount that's permitted to enter. This is a maximum quota, by the way. So you can't exceed QR, has to be greater than or equal to the actual amount produced. Right? So there's a restriction out there. Think of all the things we used to have in agriculture where farmers or intermediaries were given maximum quantity restrictions in order to keep prices high. So again, Q quota is a parameter, and it says the actual level of X produced cannot exceed that level. So in the case of the quota, we have an X, the tax equivalent rate is a variable and it's set in order to hit that maximum quota level. It could be non-binding, and you'll see that. I mean, if it could be, this is a case where effectively it's like a price being zero, which I showed them this morning with the supply and demand diagrams. Case 3 was where the supply was so large that demand price was zero. There was excess supply even at a zero price. So that can happen here. And in fact, we'll show that that does happen. This is another double loop scenario. And I guess we won't go through it word by word, but basically it does the same thing. It's going to iterate over 25 measures of something. And in this case, I'm going to use the size of the economy as the underlying parameter that's being changed. So you see that down here as we go through the loop T, the size of the economy is going to keep getting bigger. It starts with 100 units of labor and 100 units of capital, and that will be raised with each iteration of the inner loop. It will assume to be a tax rate if the OR of the outer loop, the J loop, is equal to 1, and it'll assume to be a quota if OR of J equals 1, it's 0. Yeah, you go back through the loop, and how do you unfix a loop? I guess we unfix a variable. I'm sorry, I guess we didn't mention this earlier. So it's easy to fix a variable because GAMS automatically fixes both the upper and the lower variable. To unfix a variable, you need 2 commands. You need to unfix the upper value and you need to unfix the lower value. So that's what this does when you go back through the loop. It says QR up equals plus infinity, QR low, and that's an O, not a 0, equals 0. And then you can compute what the quota is. So you solve this model. It's again, it solves 50 times or 25 levels of the size of the economy, and for 2 different variables. One is the tax rate, and well, the tax rate is fixed, I'm sorry. And one when it's allowed to be a quota where the tax is set endogenously to enforce the quota. Okay. And then again, after you get done, you can collect the results. I do that here. And there's a little extra one here, which just says, just gives the ratio of the 2 for the display results. And again, you can dump that to an Excel spreadsheet. Okay, so now back to the picture. When you make then a picture of that. This is what the picture is going to look like. Going on the screen? Pretty much so. So in this case, the horizontal axis is the size of the economy. The benchmark is equal to 1. And welfare is, again, I normalize it this time. I think I normalized it in the Excel sheet to 1 initially. So this point right here where the dotted line is the benchmark size of the economy. And so the welfare, which is the curve that's sloping downward, is equal to 1. The quota, the tax that enforces the quota is the same as the actual tax rate in the tax scenario. So welfare is the same under both the tariff and tax and the quota. And this line that's sloping down, I actually, rather than having 2 separate lines I plot the ratio. So this is the ratio of the welfare under the quota to the welfare under the constant tax, right? And the ratio is 1 at the benchmark. Now, this is interesting because what happens, this tax is purely distortionary. right? Everything, so the benchmark equilibrium is not optimal. So what happens when you make the size of the quota, the economy smaller, is that the tax that enforces the quota goes down. And since it's a distortionary tax to start with, welfare rises above the benchmark because it wasn't optimal to start with. So the upward sloping line shows the quota equivalent tax, which is 25% at the benchmark. As you make the economy smaller, the quota equivalent tax actually goes down and welfare goes up a little. In this particular example, it doesn't go up for very long because the quota becomes non-binding. So the quota tax equivalent goes actually to zero, becomes non-binding. This is sort of like that scenario in the supply demand model where price goes to zero. Okay, you have these quota licenses that, you know, there's 100 of them and people only want 50, even at a price of zero. Okay, so it's non-binding. The opposite occurs if from the benchmark you move to a larger economy, then production would naturally increase with just a tax, keep going up, it's allowed to go up. But if it's a quantity side restriction, the quantity can't go up. And the only way to prevent the quantity from going up is to raise the tax equivalent to enforce the quota. So this thing goes up, it keeps going up as the quota tax equivalent keeps rising. And there you see that the slope of the welfare curve starts going down pretty steeply because you're making the quota is becoming more and more restrictive, whereas the distortionary tax would at least allow things to keep expanding. Okay, so it's one of many things that in international trade, economists don't like quotas because if the world economy starts growing and the government won't change the quota, it just naturally becomes effectively more and more restrictive and more distortionary to welfare. So, you know, again, in the early days of GE modeling, a lot of things with non-tariff barriers were just converted into ad valorem taxes. And you can benchmark a model to the same thing so that when you run the model initially, it reproduces the same equilibrium. But this illustrates the fact that as you move away from that, with other parameters in the model changing, that the two can deviate from equivalence quite substantially. And again, the best thing is to let theory guide it as to how exactly to model some intervention like this and try to make the actual model correspond as closely as possible to reality. And from the example, you can see that it's not, in this case, it's not very hard. I mean, I don't know why they thought it was so hard in the old days, but.
Sometimes you spend a lot of time, you can imagine something that's not done properly in the model, or something that's omitted, and you'll do all this work to represent the policy more precisely and discover that, no, they made the right judgment in the first place. It doesn't really, what you thought could matter doesn't really matter. So it's not always the case that more complexity does not always introduce more insight. But that's the reason it's great to have modeling language, is you can have an idea and experiment to see what matters and what doesn't matter.
Yeah.
And if you get a good insight like this to see what, then it's very helpful. That's the reason that the thing that's hard here is that we'd like so often an input-output analysis was where this all started, but this idea that we have a fixed model that's on the shelf, just run the model through, it has everything in there. That's, I'd say that the argument often comes, my argument would be having the model there to play with and having a core model that's a starting point and then trying to experiment with different formulations and figure out what matters. That's where the real power of the framework comes.
Yeah, okay.
This is a great example. I just sent Martha an example, Jim. The thing is that, particularly for young students that are listening here, Jim is the guy you want to listen to. Because Jim always has the right keys. he's always on exactly what the right issue is and what you want to be focusing. But that doesn't mean you always want to follow these GAMS programming syntax. Sometimes there are things where those of us who are inherently sort of like, my kids have explained to me that I suffer terribly from ADD. Didn't I know about this when I was younger? I had no idea. Just sort of autistic, and I kind of like, and so those of us who are kind of like this, we're always into doing things. I get focused on the programming end of things. So I sent this an example to Martha. I guess I can. Okay, I sent around a copy of this file. So if I go here, and it's just all I called looping. And it's just like Jim's example, first example. How would I code that up? Let me set the font to something bigger. So this is the way so there's the Kia 2 model. And this is just, part of this is just a GAMS has moved along and Jim has programmed the GAMS version, whatever. It's a few years out of date. So I think that there's new stuff, new techniques, and they're also just, it's a matter of habit. Let's see if I can get this out of the way. So if you look at this, I would declare rate as being the tariff rate. I'd let it go from 0 to 125. So that gives me the tariff rates in percentage. I have the two instruments being tariff or trade cost. And then I have welfare as I define as the percent equivalent variation. This is the trick, Jim, that's come in since you've used GAMS much. Solve link equals 5. Anytime you're linking, you're solving over a loop. This tells GAMS, load the solver once in core and keep it there. So don't, and that will make it all run ultra fast. So that's a big, so anytime you have a loop. So here's the way I would loop to catch every 5. I want to only run it over 5, every 5 percentage. So I do a loop over all rates, that's from 0 to 125, but then I do a condition such the modulo of whatever the value of the rate is in 5 is equal to 0. It says take only the ones that are multiples of 5. So that'll restrict the loop to only the ones that I want to look at. And then I'm going to assign TR, and here's where Jim was made a mention. I do the conditional on the right-hand side. That means that if it's not tariff, then I set TR equal to 0. If it's tariff, I set TR equal to rate divided by 100. I solve the
I should
model.
have done it that way. Yeah.
And then I save the welfare that way. And then just a couple other tricks, dump it into a GDX file, and then I move. And one of the things I did here when I save the values, I add EPS on there. And that's a trick to make it possible that I can push through zeros to the file, because otherwise it'll drop the first number because there's no impact.
An infuriating thing about GAMS they never fixed.
No, it's a sparse matrix language, so it doesn't, they don't pass the zeros.
Stupid. You want to.
So EPS out equals 0 converts it into, converts the EPS to a 0 when it outputs it. And then I stick it out into the file. I also had, so that gives me the whole thing. And we'll see more of this tomorrow, because tomorrow I'm going to talk about running models. If you look at the XLS file, and again, this is not the debate. I love this lecture because it's like he's bang on. It's like this idea, like pay attention to what are you trying to model. This is the message. But just if you're doing the programming, there's some tricks that you can do this more elegantly. If you and the key thing, the key trick that we use here is this: be able to refer to us. If I have a set, I can't do this a set. If I had an R1 through R10, I couldn't use the dot val. But if the set elements are integers, then I can get the value back by, rather than using OR, I can say rate.val gives me back the value. So
Okay.
So rate.val says, give me the value of that index. So I'm doing the loop over the rate, and then I get rate.val back, and I divide it by 100 to convert it to a rate. Anyway, that's just some tips just for people, just to help.
Okay. No, I'll do. I like to make it as simple as possible. And thing about epsilon, so let me just tell people what the problem was. And they've never fixed this problem. If you dump a parameter into, or even if you have just the results, you have a two-dimensional parameter. If one column and or one row is all zeros, it just doesn't display. It's missing. And that's a terrible modeling decision by GAMS. I mean, that's ridiculous. If a row is 0, you want to see the zeros. You don't want it to disappear.
No, but the thing is, if you look the way I programmed this, Jim, if I put all the zeros in, I have rate defined from 0 to 125. I only want to generate the numbers from 0 to 125 for every 5.
Yeah,
So then you want to put in zeros for the reading ones, or you just omit them?
no, I don't want them to have columns and rows missing. And a
Well,
two-
the way you avoid something missing is you assign a value of Eps to everything
Yeah,
where you
I-
want something to be touched. So there I put the epsilon there. Eps says put an epsilon on, omit it if it's there, and then
No, I completely agree with your kludge here. I've used the same thing many times. I'm saying, and this one annoying thing that I don't like about
Yeah.
Canvas.
well, anyway, so there's my suggestion. And it's not to really, it's just to provide some an example. And some questions.
Okay.
So the difference between, okay, so there's an example of SolveLink, so that's good. SolveLink is mainly for these, and Jim is the one that, this idea that you get a model running and then you want to have a couple of parameters, you want to get a grid going. This is really helpful to be able to solve lots of cases when we go. This idea of being able to doing it, and I learned that from Jim. He has the number of papers. The only thing is he publishes papers in very top journals that have these grids in them where you have a lot of insight into the thing about what drives multinationals. You get a lot from being able to do this sort of managing the solver over a range of parameters is very helpful for understanding what's driving the model. So it's a good thing to know about. Great. So we're taking a break.
Right now,
Yeah.
Okay, and then we'll discuss, how long is it?
we will be back at 2:30.
Yeah, 15
Just
minutes.
15 minutes. Okay, I better figure out what we're doing next, because I'm sort of,
No, let's take a break.
Yeah, okay.